All right, so just want to mention I will be kind of working through those second Excel assignments. So I think I'm like a fourth of the way through. So start seeing grades pop up for that. And once you have a grade entered in there, it'll give you a really good idea of kind of where you're at in the course right now. But let's kind of jump into where we left off on Tuesday. So we started talking about, actually, I'll try to kind of give a setup for this. So we've got, oops, let's go to the other cam. So if we're thinking about kind of where we were starting out last class, this switches over here. There we go. So there's some variable x, and we know that it's normally distributed. It's got its own mean, it's got its own variance. So what we're going to do is convert some x value. So maybe this is like, I don't know, we're looking at height and we do 70 inches. What we're going to attempt to do is convert this variable x into z-scores, which we know have a mean of 0. Right? Once I convert this into a z-score, so we'll call this like the z-score of 70, I can look that up in the table, and the table is essentially a cumulative density function. Whatever value I look up, it'll tell me the probability of seeing that value or anything below it. Right? So we're going to, we talked last class, this was like the equation for the z-score. We simply would subtract the mean from 70 and divide by the standard deviation. But once we have that z-score, how do we use the table to find this cumulative density essentially, or the probability of seeing that z value or anything below it? So let's say I had some value and it turns into a z-score of negative 1.29. So just a reminder, that would mean that we had some value that was 1.29 standard deviations below the mean. Well, right away, if I think about this, when I turn this into a z-score, I found negative 1.29. So I want the area to the left of that. Well, right away, I know that. Well, what's the area to the left of that mean of 0? We said if it's a symmetric distribution, this mean exactly splits this in half. So there's 0.5 to the left of the mean, 0.5 to the right. So automatically, we know that this area we're finding is going to be less than 0.5. Okay. So negative 1.29 is our z-score. So I told you I'd be putting that table up there on Canvas, and should be sitting up there. It's called the z-tables, or standard normal tables. So the way that we'll use this table is we look up the z-score. First, we look at the first decimal. So negative 1.29, we scroll and we look, and here's negative 1.2. The second decimal, if we go up here, would be that 0.09. So negative 1.29, right, all the way over. So the probability we see negative 1.29 or anything below it is this value right here of 0.0985. Yeah. Oh, thank you for saying something. You're the only one here, so you're the one that needs to speak up, right? All right, there we go. So it's going to be hard to see, right? This is why I said kind of printing it out or having it pull up in front of you. What we're going to do is look up that z-score. First, look up the first decimal, so negative 1.2. And then the second decimal was that 9, negative 1.29. So we'll find where those two meet. Looks like it's right here. Negative 1.2 all the way in the last column, 9. And this value is the probability we see that z-score of negative 1.29 or anything below it. Right? So if we're thinking about essentially what that table is telling us is, well, that area we wanted, right? The probability of seeing this z-score or anything below it, right? And we're told that is 0.0985. Okay? And I'll make this a little bit bigger here in just a second, but that's kind of the area that we just identified. Right? So notice, when we look at all these negative z values, anytime we have a negative z-score, the area to the left of it should be something less than 0.5, right? Because we know the area to the left of 0 is 0.5. So the area to the left of any negative z-score is going to be something less than 0.5. Sure enough, if we look at that table, all these negative z-scores, the area to the left are all below 0.5. In fact, once we get to that point of 0.00, the area to the left is 0.5. And then if we have any positive z values, right, the area to the left of those is going to have to be something that's greater than 0.5, right, because it's going to include this area plus some more. Right? So positive z-scores should have an area over 0.5 to the left of them. Sure enough, when we look at all these positive z-scores, the area to the left, these are all above 0.5. Okay? So just kind of a review, what instead if we didn't want to look up negative 1.29, right? So we found the area to the left of that was 0.0985. What if we look up positive 1.29? So first decimal, 1.2, second decimal, 1.29. The area to the left of that is 0.9015. Okay? So if we're thinking about there what I did, and I'll kind of redraw this. I looked up that z value of 1.29, and the area to the left of it was 0.9015. As a reminder, when I looked up negative 1.29, the area kind of to the left of that was 0.0985. So one thing we'll kind of notice here is if I know the area to the left of this z-score, I can also find the area to the right, because this area under the curve is 1. So if I know the area to the left is 0.9015, yeah, we'll just subtract that from 1, 0.0985.
That goes the same way. If you know the left of that, the negative 1.29, you could have just took 1 minus that 0.0985 to get that.
Exactly, right? So if I remember this is a symmetric distribution, I know that this is centered around 0. So this should fold on top of itself. So the area to the right of the positive z-score is the same as the area to the left of that same value, but negative, right? 0.0985 on each side. Now, one thing, you could do this a couple ways, but kind of the easier way to think about it, just in case these aren't the same z-scores. Let's say I wanted the probability that the z-score is in between negative 1.29 and positive 1.29. Well, essentially, this is kind of like we did before. We did this with some of our discrete random variables. But really what I'm thinking about here is I just want to take this area, I guess I should use a different color here, and subtract it from this area, right? If I subtract the red from the blue, all I'm left with is what's in between, which is what I wanted. So essentially, it's kind of like we're taking that cumulative density function for the z value of 1.29 and subtracting that cumulative density function for that value of negative 1. Now, the cumulative density function isn't something we have to plug numbers into. We were getting these numbers by simply looking it up on the table. The table was giving me these cumulative density values, right? Or always giving me the area to the left or the probability of seeing that value or anything below it. Okay? All right. I should actually cover a couple of these next slides. So get this thing out of the way. So we already kind of went through and looked up the value to the left of negative 1.29. I showed you how to do this, just kind of a reminder slide. We looked up positive 1.29. We compared those areas, thought about, well, look, if I can find the area to the left of positive 1.29, the area to the right of it, right, should just be 1 minus that. And that's what all these slides are kind of reviewing. Oh, that's weird. All right. Just turn back on. All right. Our lights just went on and off. So we already kind of discussed this. The slide in between those, this is just going to be that, this value of 1.29, 1.65, these values start popping up a lot in the problems that we're working with, and it's because the probability of seeing something that far above the mean, that many standard deviations above the mean or less, 90%, 95%, right? These are just going to be some of our benchmark values we end up seeing a lot. Okay? So we already discussed this. I think the next one is about it being symmetric. We already talked about that, where the area to the left and the right of the mean, our mean is 0 for the standard normal distribution. The area to the left and right is 0.5. Okay? So, you know, kind of showing you this on the slides, it's really small. I'll try to pull open the PDF and zoom in a lot of the times. But as I mentioned last class, it's nice to kind of have this in front of you. So what if I wanted to find the probability that the z-score is greater than or equal to negative 2.53? Well, right away, which of these can I rule out? I mean, I look at these answers, I'm looking for a probability, can't be negative. If I draw this though, and think about, can I rule anything else out? Well, if I want the probability of being greater than negative 2.53, right? Well, if I remember the mean of my standard normal distribution, right? We're looking at z-scores. The area to the right of the mean should be 0.5. So right away, I know that this probability has to be something that's greater than 0.5, right? Because it includes this area plus some additional area. Now, if I look at the possible answers, I can rule B out because it's not greater than 0.5, but what about between A and D? Well, let's think about if A was the right answer. That would mean the area to the right of this z-score is just barely over 0.5, which would mean that it would have to be a z-score that was really, really close to 0, right? Because the area to the right would just be over 0.5. You know, we're probably not, obviously, we're not going to be real familiar yet with what's a large z-score, but when we start to think about something that's 2.5 standard deviations away, that's pretty far. So if we, last class I said, we always know that if we go 3 standard deviations above and below, 99.7% of the data is in that range. So 2.5 standard deviations is pretty far, really not very close. You know, we're saying we needed a z-score that's close to 0 to get the area to the right to be what, I think it was 5057. So it would have to be like negative 0.1. So A probably doesn't make a lot of sense. If I'm just taking a guess here, D is probably going to be the one I go with. Now, if I go ahead and look up negative 2.53 in the table, so I scroll back down here. All right, negative 2.5, 3 is the second decimal. So those two meet right here. So the area to the left of that z-score, or the probability of seeing that z-score something lower, is 0.0057. So I just found, right, the area to the left was 0.0057, which means the area to the right here, right, or kind of that, well, actually, I guess I already had it shaded, but that black shaded area, well, that's just going to be 1 minus. Yep. And that's how we got that 0.9943. Okay. So a little bit of extra work there to do when you're looking for the probability of being above a certain z-score, right? We have to subtract it from 1 there. But just kind of remembering, like drawing it out kind of helps us put a kind of a bounds on where at least where it could be. Okay. Any questions on that before we keep moving? So this should be pretty easy. What if I then ask, what's the probability that's less than negative 0.253? Well, that was literally what the table told us, right? The area to the left, that would just be the 0.0057. So I'm going to use this idea and prove to you, if we go back here, oh, where was it that I said this? There we go. Let's do this one. So let's say we're 2 standard deviations above and below. Right? Why do I know that's always 0.9544? Well, if I'm 2 standard deviations above and below, really what I'm saying there is that I'm looking for the probability that this z-score will be between -2 and +2. Right? So I kind of want this area in between the two. If I look up the z-score of 2, or sorry, -2, it'll give me this area. If I look up the z-score of +2, it would give me that area. So if I subtract the smaller one from the large one, I'm left with what's in between, which is what I wanted. So I'm going to go look up those 2 z values in my table. So the first one is -2. So this would be -2.00. Whenever I'm looking up an integer, it's -2.00. So that area to the left of that z-score is 0.0228. So if I'm just thinking about kind of labeling things here, I found this red area was 0.0228. If I then look up that z-score of positive 2, scroll down here. So 2.00, the area to the left of that is 0.9772. So let's keep the color. So that green area is 9772? So to find the areas, in between those two, I subtract the smaller area from the larger one. And 0.9772 minus 0.0228 gives me 0.9544, I think. Which, if we go here, that's what I was saying last class, right? So that's where those numbers came from. I'm gonna go kind of make this a little bit bigger so it's easier to see. If I get rid of this, right? So that's kind of where those values were coming from. And once we turn them into z-scores, when we look up that value, we're going to keep finding the same probabilities, right? So it's really about once we convert it into z-scores, that original x variable, we always know that to be between two standard deviations above and below the mean, there's always going to be a probability of 0.9544 that is the case, right? We see a value in that range. All right. So I think I'll save these for kind of the end of the class if we have a little bit of extra time. So let's think about, okay, we're starting to get an understanding of how we use the standard normal distribution. And if I have a variable that has a mean of 0 and a variance of 1, well, life is good because I can just look up my z value in the table. I can find the probability of being less than that, and I can use those to find the probability of being in between certain ranges. So what if instead we have this random variable x, and I want to know what's the probability it's in between these two values, a and b, but it's not standard normally distributed. My lights went on again. Is there like not enough movement? Oh man, that's what it is. There must be a sensor. I'm not setting off, so I'll have to be a little more animated. So the first thing that we'll do is we need to turn this normally distributed variable that has maybe a mean of 50 and a variance of 80. We need to turn that into a standard normal distribution. Well, how do we do that? We said we have that z-score equation, so I can just take this value for a, and I can turn it into a z-score. How do I do that? I just subtract the mean, divide by the standard deviation of this original variable x. I then take the value of b, I turn that into a z-score. Subtract the mean, divide by the standard deviation. Well, now I have two z-scores. I can find the area to the left of the z-score for a, the area to the left for the z-score of b, and similar to the last example we just worked through, subtract the smaller one from the larger one, and I'll have what's in between. Okay? So the steps will be kind of, first we have to get those z-scores. I always think like you don't technically have to do two, but just draw it out, kind of make it easier to see what you're looking for. Look up those probabilities or the area to the left of those two z values, and then maybe we have to do a little bit of work at the end, right? Subtract the smaller one from the larger one. Sometimes this last step, if we just want the probability of being less than a certain value, we don't have anything to do at step 4 because that's just the value we found from the table. So let's work through this with some actual values, and I'll kind of show you how I would set these up. So let's say we've got some normally distributed variable x, has a mean of 5 and a variance of 25. Right, that's how we write this normal distribution. Here's the mean, here's the variance. What's the probability I see this value or this variable take on a value that's between 10 and 15? Right? So I'm sure I have this in the slides, but I always kind of think that it's a little bit easier to see these worked out by hand. So if I was approaching this problem, what I'm thinking about is I have this variable x. It's normally distributed. Its mean is 5. As a reminder, its variance is 25. And I want to know what's the probability it's in between 10 and 15. Okay, that's what I'm looking for. So what I'm going to do is I'm going to turn this into a standard normal distribution, or make it so that I can use a standard normal distribution. So let's kind of think about, for every x value we have, we can actually map out that x value to a certain z-score, right? So I want the probability I'm in between these two. But if I just think about what would the z-score for my mean be? Well, the whole point of converting this, the fact that we're subtracting the mean from every value, the whole point of that was to get a mean for my z-score. Yep, that was equal to 0. Now, if we think about why, well, we had that z-score equation, which was just take the x value, subtract the mean, divide by the standard deviation. Well, if I plug in the mean minus the mean will always be 0. So let's say instead I want to find the z-score for this value of 10. So I plug in the value of 10. I subtract the mean of the original data, and I divide by the standard deviation of my original data, which if my variance is 25, my standard deviation is just the square root of that, or my standard deviation ends up being also 5. Okay. So this, do the math, I get a z-score of 1. Okay. Now I can do the same thing for the, so I get a z-score of 1 here. I can do the same thing for the value of 15, plug it in, subtract the mean, and get its z-score. But this one, I've got some easier numbers so we can start to really think about what we're doing. Remember, the z-scores are the number of standard deviations away this value is from the mean. So it has a z-score of 1. That's telling us it's 1 standard deviation away from the mean. Let's think about if that makes sense. If I go to the value of 10, the mean is 5. How far away is 10 from 5? 5. Our standard deviation was 5, so we were 1 standard deviation away. If I look at 15, it's 10 away from the mean. How many standard deviations is that? Just 2. Now, if I plug the values in, sure enough, I'll end up figuring, 15 minus 5 over 5. I end up getting that z-score of 2. But with these easier numbers, it's a little bit easier to think about.
You did say yesterday when we were talking about it, the standard deviations have to be equal intervals. That's it, right?
The standard deviations
have. So like the z-scores, those like, so 1 standard deviation, 1 z-score away, that's always going to be the same interval. Or no?
Yeah, so once we have the z-scores, when I see a z-score of 1, that always is telling me I'm 1 standard deviation away. Now, what the value of the standard deviation is, who knows, right? So, in an example like where I'm looking at maybe height being 5 inches away, this makes sense, right? I'm 1 standard deviation away. But if I'm thinking about, I don't know, what else would be normally distributed to a large value? Maybe something like, we could maybe, I don't think it's normally distributed, but if we think about something like home prices or something, right, where the variance is going to be much, much higher. Well, once we convert the data into z-scores, the z-scores always have the interpretation that you're 1 standard deviation away. Now, what the size of that standard deviation is, all bets are off. Yeah. Yep. Yep. All right. So I could look up that z-score of 1. Right? The table would tell me the area to the left of it. And I'm kind of circling this area. Obviously, I could be shading it in, but I always think kind of circling it makes it a little bit easier to see, because once the colors start running over each other, it's a little bit difficult. I could then look up the z-score of 2, and the table would tell me the area to the left of that. If I subtract this blue area from the red area, I'd be left with what's in between, which is what I wanted. Right? So how would I use that table? Well, let's make sure we're just getting more practice with that. So I go to my table. The first one was a z-score of 1, so 1.00. The area to the left of that is 0.8413. So this blue area kind of here, 0.8413. Right? Then I look up a z-score of 2, 2.00. We already looked at that one up earlier. The area to the left of that is 0.9772. So notice that when we look up the same z-score, we're always going to have the same cumulative density or same area to the left of it. But zoom on this a little bit more. Once I have these two values, I subtract the smaller one from the larger one, so 0.9772 minus 0.8413. I get what? 0.133 something? 359 maybe? Okay. So that's kind of how you would, work completely through a whole problem. Now, do you have to necessarily draw this part? No, but I always think that it kind of reminds you that, like, you're starting with this variable x, you're converting it into z values, you're then using the table to find cumulative density functions, And once I find this area, it kind of matches up to the original values or the original area I was looking for. Okay. Any questions on that before we keep moving? See with the chat. All right. So, a lot of that I have kind of in these slides here. The first thing we did, convert these into z-scores. That was easy enough. Then, thought about what area are we looking for, the area between 1 and 2, the z-scores of 1 and 2. I'll find the area to the left of 1, find the area to the right of 2. You can kind of see where that light blue and the bricked area cross. Once I subtract this smaller, the bricked area from the blue area, right, I'd be left with just this blue area here, which is originally what I wanted. Okay. All right, so let's start to apply this to maybe to a real data set. Lights keep going off. This is going to be a fun game the whole class. So, okay. I have this data set, and I don't think we'll get there today to work with this in Excel too much, but there is an Excel file up on Canvas that has some work that we'll be doing kind of probably mostly next week. Maybe we'll take a look at this at the end of class today, kind of depending where we're at on time. So let's say, I think about monthly rainfall. I actually look at monthly rainfall, and if I plot it out, it ends up following a pretty close to a normal distribution. And if we look at the last 100+ years of data, we can find an average rainfall, and we could find the variance of rainfall. That's pretty easy to do in Excel. If we have a column of monthly rainfall equals average of that column equals var.s or var.p of that column, depending on if we're thinking about, if we're just focused on Indiana weather and we had all the data, we would have kind of population data. But probably best to treat this as a sample since we only go back to 1895. Now we know that it varies by month. What ends up being true is if you break rainfall down by month, it looks even closer to a normal distribution. We could then find the average and the variance of, say, what is it, June rainfall here, right? If I look at the kind of graph of that, looks like it's pretty close to normal distribution. Kind of got a weird thing going here in the tail. Like I said, once you break this up by month, you start to get things that don't kind of have these extreme tails, right? Because this just is representing certain months are more likely to have more rainfall than others. Okay? So we've got kind of this nice normal distribution. And then back in 2012, there was a really extreme Indiana drought. This was kind of, a graphic that was being put out where there was very, very little rainfall and high temperatures, right? So if we kind of look at the timeline of monthly rainfall, so here we start in 2009, kind of notice like every time we hit to we're actually right about this time, like March, April, May, there's kind of this increase in rainfall, and it kind of decreases. There's a little spike here, but decreases for the most part. And then once we get to the next March, or February through June, right, it really starts to kind of increase again, kind of decreases in the winter months. We get to the next March or February, March, it increases again. Once we get to 2012, we would expect to start to see an increase here in February, March, but instead we get not get an increase, we actually get a decrease, right? So there was this, you can just see from the timeline, there's just going to be some bad year for farmers, right? And we're going to have some issues. So how unlikely was it that we saw rainfall be this low? So if you can think about, if I'm creating a product, so, specifically like this applies a lot to agriculture, but if I'm producing a product that depends on how much rainfall there is, or maybe, I'm building bridges or I'm doing some type of construction that can't be done outside in the rain, well, then I might be concerned with how likely or unlikely it is I get a certain amount of rainfall, right? So if we look at Indiana rainfall, on average every year, the kind of monthly average is 3.4 inches, and the variance on that is 2.57. So given that information, what's the probability that we saw total monthly rainfall average less than an inch or 1.3 inches like we did in 2020? So how likely was it that we saw rainfall be this low or anything lower in 2020? Well, start to kind of set this up. So once again, I'll draw this out. So I believe what the information was given, and I might have to switch back here to get the values right. But we start out with this random variable x, which is kind of monthly rainfall. Right? We're told that it's normally distributed, and it had a mean of 3.40, okay, and a variance of 2.57. Right? I then was asked, okay, what's the probability that, like I did in 2012, that I see 1.3 inches or less average monthly rainfall? Well, right away, if I think about the mean, I know the area to the left of the mean is 0.5. So this was going to be something that's less than 0.5, right? I also know that when I turn this into a z-score, before I even plug my values into my z-score equation, what's the sign of this value going to be? So if I map this out to its z-score, what has to be true about the sign of that z-score? Remember, the z-score represents the number of standard deviations, above or below the mean. So if it's below the mean, I automatically know it should have a negative z-score. Sure enough, if I plug in that value of 1.3, I subtract my mean of 3.4, and I divide by my standard deviation, which here I'm going to write it in a little differently, right? But if I had the variance, I would divide by the square root of that variance. So this would kind of represent my standard deviation, right? And then I end up, calculating what this z-score is. So that's kind of the work, right? To get to, that kind of sets us up for thinking about this z-score. So once I enter that into my calculator, I'm gonna get what here? I'm gonna cheat. Yeah, so I get negative 1.31. So we're thinking here, we just found this z-score is negative 1.31. I can look this value up in the table, find the area to the left, right? So we go to the standard normal tables. I've got negative 1.31, so can't keep everything on the same thing. But here's the second decimal. So negative 1.31. The area to the left of that is 0.0951. So I just found the area to the left, 0.0951. And for this one, I don't have a step 4 because I'm done. That's what I wanted. That's the area I wanted, right? I just wanted the probability of seeing that amount of rainfall or less. Yep, if I wanted to know what's the probability I got at least 1.3 inches of, like maybe I'm a farmer, I'm like, look, I know that we might get low rainfall, but if we get at least 1.3 inches, we'll be okay. So what's the probability that we get greater than 1.3 inches? Just 1 minus that. Yep. Any questions on that before we keep moving here? All right. So here we are, right? We looked at that z-score, find the area to the left of it. We don't really have a step 4. There's no transforming to do, right? It's just the probability we looked up. What if instead I look at September rainfall, right? I know that it's normally distributed. What's the probability that we get total monthly rainfall of less than 0.47 inches? So actually, this was how much we got this last September. So sometimes I try to pay attention to the weather and I think about using these examples for this class. So this one was pretty interesting. So on average, we get 3.25 inches of rain in September with a variance of 2.37. So we saw 0.47 last September. What was the probability we saw that or anything less? So once again, I can kind of think about, and I'll make this bigger here in just a second, but I want to make sure we can see what's on the slides and how we're mapping this out. So I draw this random, this random variable x. It's normally distributed. I know its mean is what? 3.25. And I've got a variance of 2.37. What's the probability I saw 0.47 or less? So all that was kind of information from the slide. I've got this drawn out now. I'm thinking about this random variable x. Well, what I'm going to have to do is map this out to a standard normal distribution and figure out what z-score this corresponds to. So once again, we'll take the value we're interested in for x, subtract the mean, and divide by the standard deviation. So I've got what? 0.47 minus 3.25, which was the mean of that original x variable, and then divide by the standard deviation of that original variable. Now, what I could do before, I plugged in the square root of the 2.37, the variance. What I could do is first calculate that. So I actually don't have it off the top of my head, so I'm going to use Excel to cheat here real quick. Do some math for me. So this is what equals square root of 2.37. So about 1.54. All right. So we've got a standard deviation of about 1.54. So we'll divide by that. That will give us this z-score value. So if we plug that into our calculator, we should end up with about negative 1.81. Okay. So if we plug that into our calculator, we get about negative 1.81. So we plot that, found our z-score. Now it's just a matter of looking it up in the table. The table will tell me the area to the left. Okay. So negative 1.81. And we'll start to notice, like, we're getting close to being 2 standard deviations away, so this shouldn't be the most likely thing. So negative 1.8, and we kind of remember here's the second decimal of 1, so negative 1.81. The probability we saw that low of rainfall in September, or that we saw something less, is 0.0351. So that's kind of, sorry, I wasn't thinking there. I wanted to go back to the slides. Here we go. All right, so I looked that up, and it's a pretty low probability. And that's because being almost 2 standard deviations away from the mean, right, that's what that z-score interpretation is actually pretty far, right? Being anything more than 1 standard deviation away from the mean, you start to get some lower probabilities. Once we get out to like 2, they start to become really small. And in fact, if we look at the table, what happens once I get like 3 standard deviations away? Well, now the area to the left of that is, really, really small, almost 0, right? By the time we get to negative 4, it basically, the 4th decimal looks like it's 0. Okay, so being 3 or 4 standard deviations away from the mean is very far. Being 1 or 2 is, still not, still going to have some relatively low probabilities associated with it. And like I said, as we do more of these, we'll start to kind of recognize the values. If it is really far away from the mean, we know the area to the left is close to 0. And that just comes from having a little bit more practice kind of working with these z-values. Okay. All right, so went through this example. We could break this down into a bunch of different kind of months, right? The different months have, different notice here, the variance in June temperature is much lower than in February. So, even though we have means, right, there's going to be a lot more variation in February temperatures than there are in June. So we could break this down by month as well. So let's say the average June temperature in Indiana is normally distributed with a mean of 70.75, variance of 6.3. Right? Guessing this is in Fahrenheit. So what's the probability that we see an average temperature be greater than 71.4? So once again, I'll try to kind of keep this up on the screen here and start this problem out, and then we'll kind of zoom in on it. So we've got this normally distributed variable x, which represents temperature, has a mean of what? 70.75 and a variance of 6.3. Okay. We then said, what's the probability we see 71.4 or greater? Okay. So right away, right, what do I know that this area has to be greater than? Well, if I think about the mean, the area to the left and right of the mean should be 0.5. Okay. So I can see this is going to be an area that is smaller than 0.5. Okay. So I look at the possible answers I was given there. A and D are the only ones that make sense, right? Because it has to be an area less than 0.5. From there, I'm going to map this random variable x to z-scores. What I'm thinking about there is, once again, hopefully like I'm kind of hammering this into you today. But all we do is subtract the mean. So we look at the value x I'm interested in, subtract that mean, 70.75, and divide by that standard deviation, which we have the variance, so divide by the square root of the variance. Any questions on that? Once again, I'm going to cheat because I know this is in the slides, but that's not what I want. Oh, there it is. 0.259, right? So 0.259. So my z-score is 0.259, which is going to present some problems to me. When I go to look this up in the table, what's going to be the issue? Table only goes to the second decimal, right? So anytime I come up with a z-score, I'm going to have to round it to the nearest second decimal. So we're going to have to look up what? Yeah, 0.26. So we go to my table. Right away, when I look at that z-score, if I was looking at these, which of these answers makes more sense? So we know the area is going to be smaller than, or wait, I might have said that backwards when I was explaining it earlier. We know it's going to be smaller than 0.5, so we can rule out B and C. Sorry, I think I said A and D, but I meant A and D are the only possible answers there. So if I'm looking at a z-score of what, 0.26, that's really, 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 like the way I drew it, like I didn't know ahead of time what the z-score was going to be. But if I think about, you know, the mean of this standard normal distribution is 0, 0.26 is going to be really, really close to that. So I'm thinking, even though I know the area is going to be less than 0.5, it's probably going to be pretty close to that, right? Or at least it's going to be closer to 0.5 than the area is going to be to 0, right? So if I'm guessing here, and I'm looking at the only answers that make sense are A and D, probably going to guess A. But I can go ahead and work it out. So I look up that 0.26. So yep, 0.26, so 0.6026. Right? Now I have to remember that gave me the area to the left. I wanted originally this area to the right. So I'm going to have to do 1 minus that, which just gets that, what, 0.3974. Okay. And then I'm done. So that like 1 minus, that's like step 4. That's like my transfer the use the probability to transform them, right? Depending on what I want. Okay. So, you know, not that unlikely, right? Given the average temperature and the variance, not very unlikely for us to see a temperature as high as 71.4. So 2017, going back a couple years now, we actually had an unseasonably warm February. It'd be interesting now that February's over, I could probably redo this example with, I don't know, this month's average. But in 2017, it was an unseasonably warm February in Indiana. So usually the average is about 29. We've got a pretty high variance. So what's the probability we see, you know, an average temperature in February will be 42 or greater, right? So it's the same sort of setup. We're just replacing the values that we're looking at. So go here, kind of set this up looking at these values. So I've got February temperature now. That's my random variable x. It's normally distributed with a mean of 28.89 and a variance of 26.16. I'm asked for what's the probability that it's 42.85 or greater. Okay. Now, right away, if we think about comparing this to the last example, which we could do, but you know, if I think about the values here, it's the same sort of setup, right? I want the area to the right of a certain value. Well, before, we were relatively close to the mean, right? And you might think, well, now we're what, 14 away? We're pretty far away from that mean. This is going to be a probability that's pretty close to 0 because this has to be like, have a really high z-score, like it's way far above the mean. The problem is, part of that z-score is using the standard deviation. And if we compare the standard deviations, well, this one was much lower, or the variance is a standard deviation. This one's much lower. So I don't really know how many standard deviations away this is going to be. I'm actually going to have to calculate it. So, well, I shouldn't have done that because I wanted to map this out. Hold on. Should have done the work a little bit lower. No, you're okay. So I map this out to a z-score. I want the area to the right. So I take the value I'm interested in, 42.85, subtract the mean, and divide by the standard deviation here. Well, just ahead of time, if I do this, if you want to help me out, I'd appreciate it. Standard deviation will be the square root of 26.16, which is approximately what? 5.1-ish. So if I look at this, I'm about, almost 3, somewhere between 2 and 3 standard deviations away. I'm about 13, 14 away. Standard deviation is 5, so it's going to be close to 3, but not quite, right? I think if I end up doing this, I probably get 2.73. So if I divide here by 5.1, I get that 2.73 z-score. When I look that up in the table, so look up 2.73. So scroll down here. Sometimes it's easier. So the second decimal was the 3, right? So 2.73, go all the way down. 2.73, 0.9968. Right? So remember, the table always tells me the area to the left. I wanted the area to the right, so I have one more step, which is to subtract that from 1. So we end up getting something pretty close to 0, and that's because even though the variance was really high, we were still we ended up still being what? Almost 3 standard deviations away from that mean. So, the probability that it was as warm as it was in 2017 in February, at 0.0032 or a 0.32% chance. So pretty unseasonably warm in that 2017 February. And you can start to do this really we could do this every month. Like I said, we could basically do the same sort of setup. I don't know, I've done this before. So let's go Indiana, February 2021 average temperature. So usually weather has a summary of it if the month is over, but I don't know if it's past that enough. So let's say the average temperature. No. Oh, this is just all about India. Let's see. Weather spark. Okay, so daily, blah, blah, blah. Reference. We can look at the last February. Well, if we did a little bit more Google searching, I'm sure we could find. I know there's a source. Maybe it's AccuWeather, and it'll give you every day. Yeah, so I could basically go and take the high of each one of these days, and then find the kind of what the average temperature was this February. It'll be influenced a little bit by this last week since it was so nice. But you could then start to just essentially plug in different values here and see how likely was it that it was this warm or this cold, right? You could do the same kind of thing. And weather data, but how exciting can it be? But it is kind of interesting to find these things. So, what do I want to do for the rest of today? I think we're gonna hold off on Excel till next week, but I think we'll go through. I think we'll introduce this idea of the inverse transformation, and we've got enough time. So, all right. So all these examples we've been working. Kind of starting out with a value for x, turning that into a z-score, and then finding the probability we saw something that far away from the mean, or that far or even further. Okay? Well, we can actually work backwards, right? So let's say we've got this z-score. Right? What if I start out knowing the probability I want and want to find the x value that gives that to me? So think about before what we were doing. Was I was starting out with a value for x, and then eventually I was finding some probability, right, of seeing that value or greater or that value or less. But what if I start out knowing that I want, I don't know, 0.0032 in this tail? What x value would give that to me? So I start out knowing the probability. I can work backwards and find the x value that would give me that probability. So to do that, all we're going to do is solve for x here. So I just rearrange things that whatever x value I want, I can find kind of what this cutoff value is, and this z-score really is going to be synonymous with a certain probability, right, or a certain area to the left. If I think about going back to this table, every single, if I wanted to look up any area to the left, like let's say I wanted the area to the left to be 0.9099, well, there is always going to be a z-score associated with that. So you could almost think about it as when we're talking about these z-scores, like it's going to be, there's some z-score associated with seeing, 0.0991, right? Or a z-score associated with seeing whatever area to the left that we desire is. So with this inverse transformation function, kind of show you how we can use this and work backwards. So let's say we've got a test and it's distributed normally with a mean of 72 and a variance of 64. What's the lowest score? That will be in the top 10% of the distribution. So if we think about what we're looking for here, we have to kind of find the z-score that would give us the cutoff where we're looking at the top 10%. Okay? So I'm going to draw this out. Okay? What we know is we've got this z-score, and we want to find what that z-score is that would give us kind of 0.9 to the left, or, right, that top 10%, 0.1 to the right, right? So this is kind of the setup, right? What's the cutoff for kind of z-score where it would separate it to where we have an area to the left of 0.9, area to the right of 0.1. Now, what we know is that z-score can be mapped to a certain x value, right? We know the mean up here, I think, was 72, and the variance was 64, which would give us, what, a standard deviation of 8. So what I can do is say, well, look, I can go to the table. I can use it in reverse. I can look up the area to the left, which is 0.9, find the z-score. Once I have that z-score, I'll then have all the components I need to solve this inverse transformation formula. Okay? Because I already know the mean, I know the standard deviation, so now it's just finding that z-score that gives me 0.9 to the left. Right? So the way you use that table in reverse is now you're not looking up one of the z values, you are now looking up this area to the left, right, or the cumulative density that you want. So I searched through these numbers and I said, okay, what's closest to 0.9? Okay, in between these two values, right? So I can't get exactly 0.9, but what I can do is I can say, well, look, I know the area to the left of 1.28 is 0.8997. And I know the area to the left of 1.29 is 0.9015. So, theoretically, we could do some interpolation, but the way that we'll kind of approach it in this class is if I'm in between two values here, I'm just going to err on the side of caution. I'm always going to take the higher of the two, right? So it doesn't matter, whatever two I'm in between, take the higher of the two in absolute value, right? So 1.29, right? So once I have that 1.29, I know that's the z-score. That gives me about approximately 0.9 in that lower left tail. Now I can plug this value in, and now I can compute what that x value is. Right? So it's going to be what? Right around 83 or something like that. Yeah, so let's see what the exact answer is. Once we plug everything in there, we get about 82.34. Right? So I think maybe it starts helping, on one like this, draw out kind of what you're looking for with those z-scores. You need one of the top 10% cutoff. And then kind of draw out the original variable x with its mean. You're kind of thinking about, I'm looking for some value that is, first of all, if we know the mean is 72, and we look up that z-score and it's 1.29, we automatically know this value should be 1.29 standard deviations above that mean. So we should be thinking about a value that's above 72 at the very least, right? If we're just trying to put bounds on things. But once we plug everything in, we can get that exact x value of, what was it, 82.39 or something like that.
So I know when I did it, I did 8 times 1.29 plus 72.
Yeah.
And it's literally off 0.2. We would just assume that it's supposed to start answering at that point.
So what did you end up getting?
83.32. The answer is 83.24.
83.
I mean, it's very, very small.
So
82.
yeah, so I'm guessing what I did here. So we're setting this up. I probably used exactly 0.9. So I probably just took this out to a further decimal because I was using some stuff that we'll talk about next week with Excel where you can actually get further than 2 decimals, right? But yeah, that's probably why I was a little off. So like if it's on the exam or something like that or on an online quiz, I'm not going to have 2 answers that are really close to each other. So if you're really close, like within a decimal or so, like that'd be the one that you assume you probably did it right. But as we work through some of that Excel stuff, we can get a little bit more exact here. Got time for this last one. So let's do a similar type of inverse transformation. Same sort of setup, same exam scores. But now I want the score that would be kind of the lowest score I could see in the bottom 40%. Or essentially, what's the cutoff for being in that bottom 40% or top 60%? Right? So what I'm thinking about here is what I'm going to have to do as part of the inverse is I know the area I want in the lower left tail is 0.4. I can get this here. And I can actually go, I usually draw the x variable up top, but it doesn't matter which direction. So what I've got here is my standard normal distribution, and I know I'm looking for the z-score. That's the cutoff for the bottom 40%. Right? Sorry, not x. So what is that z-score? That would give me 0.4 in the lower left tail. Okay. So I go to my table. First of all, if I think about these answers, before I even go to the table, right, I just look at these possible values. Well, I know that at an area of 0.4, if I'm thinking about this variable x, it has a mean of 72. If I know the area is 0.4, that's going to be some test score that's less than the mean, right? Because if it was the mean, it would have an area of 0.5 to the left of it. So right away, I know I'm going to be looking for something less than 72. So I can rule out B. Now, A and C, if that was the score, I mean, first of all, if I'm thinking about a test score, negative 0.26 doesn't make a lot of sense. If I had a test score of 0.26 when the mean or the average was 72, well, that should be like the cutoff for the bottom 1%, right? So if I was thinking intuitively about this one, I know it's probably going to be D, but how can we actually get that, right? So I look up that area that I wanted in this lower left tail, which was that 0.4. So I don't look up 0.4. That's not my z-score. That's the area that's in that tail. So I go through, I hunt. I'm gonna have to get rid of this so we can see this. So where's where's 0.4? Looks like it's in between these two. So in between negative 0.2, go all the way up, 5 and negative 0.26. So once again, I'll take the larger and absolute value of the two. So negative 0.26. So I've got negative 0.26. Is that z value, right? Remember, if we recall, the variance was 64, which made the standard deviation equal to 8. So if I'm trying to solve for what x value would kind of be that cutoff to have 40% of the scores below it, I use that inverse transformation function, which is just take the mean, add the z-score times the standard deviation. When my mean 72, that z-score was negative 0.26, and my standard deviation was 8. Right? So if I do that, I'll get 69 point something. Okay. So if I go here's double check, 69.92. Okay. Any questions on that one? So it's really like we're just working in reverse. And so instead of looking up on the row and column heading to find your z-score and then your corresponding probability, well, now you're looking for the probability and then going over to the row and column heading to find your corresponding z-score that would give you that area in the tail or give you that probability. Okay? All right, so I think we'll save the Excel stuff. Save that for next week. Let me see, I wanted to go back and point these out. I don't think I got to these at the end of last class. So I just thought these are some interesting examples. So I mentioned that we see the normal distribution pop up all over the place, especially in nature and kind of these biological markers. So here I had this like data set of 12,000 people. It was survey data. So like, you know, this is reported height. But you can kind of see like it follows really close to like a pretty nice normal distribution. So that's why we think of the human height being normally distributed. I also like happened to follow this thing that was it's like a fitness related thing, but they had some CrossFit Games stuff up there, or like some like it's to do like these open workouts to like make it to the games. But they had whatever this workout was, I don't remember which one it was. They had the female and the male data kind of graphed out here, and like they were geeking out about, I don't know, something about how many reps people did or something. But I saw it and I was like, look at how perfect of a normal distribution this female data or this female human performance was on this one particular workout. I mean, this is like, I couldn't draw it freehand, you know, better than this. And, you know, the male data is a little off, but it's still pretty close to like a normal distribution here. So once again, a human performance measure where we see kind of this normal distribution pop out. I also had this huge powerlifting data set with like all these different powerlifting meets across the country, and then all the people's performances and their age and stuff. And so I kind of put some parameters on it. Like I didn't use everything here. Like I cut out kids and really old people. But, you know, looking at these distributions, it ends up being, if I look at this one lift, turn on lights. Maybe they gave up on this. Let's see, there we go. All right, my lights cut out again. So I looked at this one lift, which was deadlift, and just kind of the total weight that was lifted, right? So, you know, these are really a little bit skewed here, but I mean, pretty close to a normal distribution, maybe a little bit of right skew, but really close to a normal distribution. And a lot of what's happening with this right skew, these really extreme values, these are also going to be, you know, I'm comparing people here that weigh very different amounts. Okay, so likely these individuals are just very, very heavy. And I started to think about, well, if I look at the averages, right? So what's something that defines our normal distribution? So this looks like the average is around 350 maybe. And the average here is somewhere closer to like 600. So kind of the male, you know, weight lifted is significantly higher, right? But, you know, I don't know, I always have this interest in like, this isn't capturing everything, right? Because when you start looking at the data, there's a lot fewer 300-pound plus women than there were 300-pound plus men. There's actually quite a few 300-pound plus men in the data set. So, well, yeah, if I weigh 400 or 500 pounds, I'm probably able to do a little bit more weight on this lift. So they have this thing which is called the Wilks, which essentially the easiest way to think about it is you simply divide the weight lifted by the person's body weight. So you're getting like a per pound lifted kind of measure, right? A kind of better statistic that's incorporating or controlling for like differences in weights. So when you do that, first of all, these go from like being really skewed to, I mean, the male per pound or, you know, per pound of body weight lifted is very, I mean, this is a perfect normal distribution. You could maybe argue the women's has a slightly longer right tail, but it's really, really close. And, you know, if I'm thinking about the averages here, and I forget, I calculated and looked at them, but this one's about 350, right, somewhere in the around 350 Wilks. And then this one is it's under 400 by a bit, so maybe I think it's like 370, but pretty much very, very close, like a lot closer than we were thinking about comparing the weight lifted. So if I'm making some statement about, you know, men are stronger because I look at the numbers here, well, okay, yeah, but if you're trying to argue that there's like some innate difference in strength, it's probably a lot more linked to body weight, because once we control for that, female and male kind of performance per pound of body weight lifted looks very, very similar. Right? So that's always kind of an interesting example, kind of, you know, incorporating a lot of things that we're talking about, but also seeing just really nice normal distributions pop up naturally, which is pretty wild. And then I'll leave you with one meme. There's only one of you, and I guess there's people on Zoom, but there's one of you who can kind of enjoy this in class. But if hotness was a normal distribution, you'd be 3 standard deviations above the mean. I always thought this was like the best pickup line. Or you could say that you'd be a z-score of 3. If they don't know what that means, then you're like, well, it's not worth my time anyway. So we'll kind of pick up, do some Excel work on Monday. I'll show you kind of this little Cubs example that I have, but also working with a data set where we're using that Indiana weather, okay? So we'll do that on Monday. That Learn Smart is due before we meet on Tuesday. The Learn Smart is due before we meet on Tuesday as well, so make sure you go on, get that done. Shouldn't take more than 10 minutes. And other than that, I think that should do it for me. I will see you guys on Thursday, or Tuesday. Today's Thursday. I'll see you guys on Tuesday.